Here's a QOD video that is about a aspect of gas laws known as Dalton's law of partial pressures. So this is the same guy, John Dalton, who came up with the atomic theory. He was also interested in understanding gases. And actually, a lot of the early chemists who did a lot of the early sort of chemistry breakthroughs in the 18th and 19th centuries were working with gases, including Avogadro. So what Dalton's law of partial pressure says is the total pressure of a mixture of gases is equal to the sum of the pressures that each would exert if it were present by itself. And so let's think about what that means. We've already kind of learned, as you've maybe grasped this so far as we've been talking about gases, that gases have properties, pressure, volume, number of moles, temperature, that are independent of what the identity of the gas itself is. So if I have a mixture, say, of helium and neon and hydrogen, and I know how many moles of each I have, I can find what the pressure due to just hydrogen is in that mixture by using the number of moles and the volume and the temperature and calculating a pressure using the ideal gas equation. Then I could do the same for helium. Then I can do the same for neon, and I could get pressures for each of those three gases. Because they're part of a mixture, we would call them partial pressures. And the pressure of the total mixture is simply equal to the sum of the partial pressure. Now let's think about this in terms of something a little bit more concrete. Air. So if P total for air, for example, is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3, etc. Well, we can really think of air as being made up of three things primarily. Air consists, 99.9% of air is nitrogen, oxygen, or argon. And so we can say that the total pressure of air is equal to the partial pressure of nitrogen in the air sample plus the partial pressure of oxygen in the air sample plus the partial pressure of argon in the air sample. Well, do they all contribute equally to the overall pressure of air? Well, they don't, and I think you can just kind of tell intuitively that they wouldn't, because nitrogen is there in much greater proportion than oxygen, and oxygen is there in much greater proportion than argon. As it turns out, the partial pressure of a gas in a mixture is proportional to its mole fraction. And mole fraction is a term that we've come across just once before when it had to do with an automobile engine and the mole fraction of oxygen in air. But mole fraction, which is given this Greek symbol chi, the mole fraction of a substance is equal to the number of moles of that particular substance over the total number of moles in the mixture. So this is typically used for gases when we're talking about mole fraction. In other words, the mole fraction of substance A is simply equal to the moles of A present in the sample plus the total moles of gas present in the sample if we're talking about gases. And the pressure of A, the partial pressure of A in the sample, is equal to the mole fraction of A times the total pressure of the sample. So let's go on to our air example and see what that means when we work that out. So air is composed of 78% nitrogen, 21% oxygen, and 1% argon. Determine the partial pressures of each of these gases in a sample of air that is at 1 atmosphere. Again, the two things. The mole fraction is the moles of the substance we're thinking about over the total moles present. And the partial pressure of that gas is going to be equal to its mole fraction multiplied by the total pressure of the gas. Well, the mole fraction, we just said, if these percentages are not by weight, they're by number of particles or by moles of particles. And so therefore the mole fraction, so what we're really saying is that if we've got 100 moles of air, 78 moles of that is nitrogen. So that would be moles of nitrogen present, 78, divided by total moles, 100. That gives us a mole fraction for nitrogen of 0.78. The partial pressure due to nitrogen is simply equal to its mole fraction multiplied by the total pressure, and in this case we said it's air at 1 atmosphere, and therefore the partial pressure of nitrogen in that mixture would be 0.78 atmospheres. For oxygen, it would be the 0.21 that we get from the 21% times the total pressure would give us 0.21 atmospheres. And for argon, it would be 0.01 because it's 1% times 1 atmosphere, which is 0.01 atmospheres. And if we add these numbers up, we get 1 atmosphere, 0.78 plus 0.21 times 0.78 plus 0.21 plus 0.01 is equal to 1 atmosphere. So that seems actually fairly intuitive and straightforward. Let's look at an example that is not that much more difficult, but slightly more difficult. And that is, we have a mixture of xenon, krypton, and argon, and that mixture has a total pressure of 6.7 atmospheres. What is the mole fraction of krypton in the mixture if the partial pressures of xenon and argon are 1.6 and 2.8 respectively? In other words, the total pressure is 6.7, partial pressure of xenon is 1.6, the partial pressure of argon is 2.8. What is the mole fraction of krypton in that? Well, the way to solve this is to start by calculating the partial pressure of krypton in this mixture. So just adapting our partial pressure equation, if the total pressure is equal to the sum of the partial pressures of all the constituents, then the total pressure of this mixture, 6.7 atmospheres, is going to be equal to the partial pressures of all the constituent gases. Well, it gives us the partial pressures for xenon and argon. So I can rearrange this equation so that the partial pressure of krypton is equal to the total pressure minus the sum of the partial pressures of xenon and argon. So we plug in the numbers that the problem gives us. The total pressure is 6.7 atmospheres. The partial pressures of xenon and argon are given to us as 1.6 and 2.8. We get the partial pressure of krypton is equal to 2.30 atmospheres. Okay, we've worked out the partial pressure of krypton. Now we want to try and work out its mole fraction. And so we go back to the equation that I gave you earlier, which is that the partial pressure of any substance in a mixture is equal to its mole fraction times the total pressure. So we can substitute in krypton for just generic substance A. Partial pressure of krypton is equal to the mole fraction of krypton times the total pressure. We want to solve for the mole fraction of krypton. That's going to be equal to the partial pressure of krypton divided by the total pressure. On the last slide, we worked out that the partial pressure of krypton was equal to 2.30 atmospheres. The total pressure is 6.70 atmospheres. Therefore, the mole fraction of krypton in the mixture is 3.43. You might be wondering, what's the purpose of all this anyway? Why do we care what the partial pressure? If I've got a mixture of gases, why do I care about what it's made up of and which gas is contributing how much pressure? Excuse me. Well, that begins to matter when we start discussing things like we will later in the year about equilibrium and kinetics, which are dependent on concentrations of things. And so we need to be able to break down a mixture of gases and know not just what the total pressure of that mixture is, but what the partial pressures of its individual components are. There's one more bit that we want to talk about, and that is the idea of when we collect a gas over water. So here's a schematic description of a little experiment that we did. We've already done this week in first period. We'll do it at the end of the week in seventh period. But this is generating hydrogen gas by reacting zinc metal with hydrochloric acid. That generates hydrogen gas. We run that through a tube, and then we collect it. In the case of our class, we were collecting it in a graduated cylinder to measure its volume. But in the process of doing that, it's passing through water. And what that means is, and water is somewhat volatile, which means it will vaporize to a certain extent. That gas that we're collecting above the water surface doesn't just have hydrogen in it. You'll see there's some hydrogen molecules here. It also has some water in it because water vapor is going to comprise a certain percentage of that. And so it kind of shows an exaggerated view of this. There's not that much water. Here there's like 1, 2, 3, 4, 5, 6. There are 3 water molecules for every 6 hydrogen molecules. That's not true. But there is a certain component of this gas pressure that is due not to hydrogen, but is due to water. And so why is that important? Because when we're collecting something, when we're collecting a gas over water, because there's water vapor mixed in with the gas, in order to do quantitative calculations involving that volume of gas that we've collected, we have to subtract out the vapor pressure of the water, which is the partial pressure of the water, from the total pressure of the system. And so that partial pressure of water, the pressure of water over liquid water, is what's known as the vapor pressure. And there are tables of this. There's a table in the back of your textbook in Appendix B. This is not the image from Appendix B. This is just something I found online, but your textbook has Appendix B. And what this is, because the vapor pressure of water is actually a temperature-dependent property. And so it varies excuse me, as the temperature goes up, the vapor pressure of water goes up. And what's nice about the table in the back of your book is that when it gets to about 15 degrees, it starts going every degree and telling you what the vapor pressure of water is. And so every degree between 15 and 25, it'll give you that. And so that makes it useful for doing certain types of problems. And so let's take a look at a problem where you might have to employ this. So I've just written this problem to mimic what we did in first period earlier this week, and that is we generated 800 mils of hydrogen gas, and we collected it over water, and we looked at the thermometer, and we found that it was 21 degrees in the room, and we just assumed, because my barometer is broken, that it's 1 atmosphere of pressure. How many moles of hydrogen gas were collected? Well, if we weren't accounting for the vapor pressure of water, we would just do it this way. We're solving for moles. N is equal to PV over RT. We're going to just put in all the variables that have been defined for us here. The pressure is 1 atmosphere. The volume of gas we collected was 800 mils or 0.8 liters. The gas constant is a constant, and the temperature is 21 degrees, which is 294 kelvins. And we would get an answer that we had made 0.0331 moles of hydrogen. But this does not account for the fact that a small portion of that gas sample we collected is not hydrogen, but is water. And so how would we actually do this? We would start by doing a correction to the pressure term. So 1 atmosphere is equal to 760 torr. If you look in the back of your book, what you'll find is that at 21 degrees, the partial pressure of water is 18.7 torr. So we subtract that out, and now it tells us that the actual partial pressure of hydrogen in there is not 1 atmosphere, but 751.3 torr, which we can convert to atmospheres simply by dividing by 760, and so that becomes 0.989 atmospheres. Now we plug that into the same equation, but instead of this being a 1, which is the total pressure, including both hydrogen and water, we use 0.989, which is just the partial pressure due to hydrogen. And that gives us a slightly different answer. Instead of 0.0331 moles, it's 0.0328 moles. Now that's a pretty tiny difference, but it will vary more with at increased temperatures at which the vapor pressure of water is higher. And you're likely to see a problem either from me or from the College Board in which it asks you to solve a problem like this, and in which one of the intentionally wrong answers would be 0.0331 moles, and the correct answer would be 0.0328. Okay, that's the end of our video. Look for, I'll post some practice problems along with this, and there will be a QOD to follow. Thanks for watching.